Good morning, everyone. A very quick check before I start. Are you able to hear me? Can I get a response on chat? Yes, no, please. Okay, thank you. Thank you so much. Thanks for confirming. So let's start. Thanks again for joining this morning. And my name is Pranjal, and hello from Singapore again. So this the topic of the today's session is introduction to deep learning. The way that how we are going to conduct this session would be more on the hands-on part again. So basically this we are going to see what is deep learning, and then how it is different from actual machine learning. So it's a basically advanced form, very core technology that what we are going to use. We'll see different libraries which we use in the deep learning techniques. We are going to use some notebooks, Jupyter notebooks, to see how we can write the code, how we can get the output, how we can get the results using some of the use cases and some of the data, right? So this is what we are going to see. Let's see. I hope we at the end of the session you will be at least able to know some of the good libraries which we use very frequently, and how these things are important, right? So again, so let's continue from here. Okay, so first of all, if you have any queries, how we are going to interact. So again, the chat, and I know everyone knows this thing because I already got a response. So yeah, this is the chat functionality we'll use in the Zoom, and we will try to answer all your queries later also at the end if you have anything. Okay, so from where you are dialing today, just a quick check. You can name the place from where, which country you are from. Okay, got India, USA, Singapore. Hello, neighbor. Hi, Marine. Hello. Hi, God. So most of us here are from India. So I think it's just as almost same 2.5 hours of the time different. And thanks again for joining from other parts of the world. I know it's a different time zone from there. So thanks again for taking your time out for this. Let's quickly discuss about first who we are here. So we are Exaltius, and we are a technology and data driven company. The main things that what we do is all mostly towards the data side. So our expertise lies in the data engineering part. We do data analytics, the data science. We use big data platforms, cloud technologies, and all. For all the companies here and also in the Southeast Asia regions, we provide them the software solutions using the machine learning and algorithms, and also create the AI platforms for that based on their needs. So we first get the requirement, and then they build the platforms for them. In terms of the training side, we have conducted a lot training. Actually, this data is again old, so we have conducted more than 1,000 training sessions across Southeast Asia region. And this was mostly because of the COVID situation, which we moved to the online sessions, and that's why the numbers are actually is increasing on a daily basis, right? All of our trainers are from industries. So the data sets, the way that how we should approach, we always do according to the to want to solve the real business needs. Okay, so this is how it's little different from the exactly the academic things. The clients that what we serve here are from different domains, be it your banking like UOB DBS here, be it your different retails like NTUC, Fair Price and all, or be it your universities like NUS, NTU, SMU, Kaplan, and all these different universities. So we cover actually in all these domains and all the others as well. Some of the glimpses of our past sessions when we are doing the face-to-face trainings here are these. Right now we move to online sessions. So thanks again to technology, thanks again to Zoom platform, and best all of first of all thanks to the internet that we are actually able to connect here today also. Okay, so without taking much of your time, I will hand over to our speaker, Mr. Fan. So let's hear from him directly about the real content. So thank you everyone. Happy learning and enjoy. I hope you'll all enjoy the session. Okay, Fan, over to you.
Okay, thank you, Praja. Okay, can you guys see the slide? Okay. Hi. Good morning. Good afternoon. Good evening. My name is Fan Ying Lun. Welcome to this session on the introduction to deep learning. Now,
Sorry, a quick check. We cannot see the slides.
oh, sorry. Let me check again. Hmm. Oh, my bad. Okay. Can you guys see it now? Panja, can you see it?
Please put in presentation mode. So you can see, please put in presentation mode.
Can you see the slide now?
Yes, can see. Can you please
Okay,
put
good.
in the
Thank you.
presentation mode?
Okay. Sorry for the delay. Okay. Now, thank you for joining the session. So this is the introduction to deep learning on a high level. So today we'll talk about what is deep learning, what are some of the applications that are out there, and what can you do with it, right? And how do you apply deep learning? So now, deep learning is a way to teach machines to perform tasks without explicitly programming them to do so. Okay. Now, deep learning is part of computer science of making machines that think or act rationally to surrounding and environment. Okay. Now, where do we apply deep learning? Well, basically it's everywhere. You see in uh, natural language, whereby you see in Google Assistant with your phone series. You also see in multiple products on the website, even on your phone, tablets, whereby you can do question answering, translation, even your web search. These have deep learning running on the background. Now, it also can be applied in images and visions, especially in the area of object and face recognition, and also in famously in image classification. Of course, it also in heavily used in areas of robotics. Think of the self-driving cars. And finally,
Hello.
sorry, yes.
Sorry, Fan, just to interrupt in between. Can you please put your slides in just presentation mode? We can see two screens. That's why it's very
Oh, sorry.
small.
Oh,
Yes,
okay.
please do it.
My bad, my bad. uh, okay, just a second. Mm,
Just wait for a while, guys. Sorry about it. Again, uh, sometimes new technical things help us also, and sometimes it create issues also.
so
I
sorry
think
about it.
Mr. Fan
Is
is
this
just
better?
trying.
Is this better?
Yeah, but still it's not in presentation mode.
It's not.
You can just start the slideshow. That's all. Can you see on the top slideshow?
Okay.
Yeah, on the top you can see the slideshow options.
Yeah.
Yeah, awesome. Can I start?
It's better?
Yes, can I start, please?
Okay. Okay. Yes, I was saying, beside in robotics, last but not least, you do see it now showing up in the gaming world. Uh, Most importantly, one of the biggest breakthrough was during in 2017 when AlphaGo managed to beat for the first time a professional world champion nine-dan player, and then history become what it is today. It even make breakthrough in other games like Dota and other kind of RPG game. Okay, so now deep learning is kind of a mix of philosophy, the knowledge of philosophy, biology, psychology, mathematics, and computer science. But fundamentally, it relies heavily on the three uh, 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 things, which is the maths, the computer science, and uh, and the big data that we have out there. So now, deep learning rely heavily on the uh, concept of a neuron, which is based on the actual biological neuron in the human brain. So um, and on top of that, it also depends heavily on the maths that drive it, fundamentally in the area of linear algebra, uh, matrix, and calculus. Now, deep learning is actually a subset of machine learning, which in turn itself is a subset of artificial intelligence. So before I move on, let's uh, understand a little bit between what is artificial intelligence, machine learning, and neurons, etc., etc. So now, artificial intelligence is a subgenre of computer science which teaches the machines to act rationally to its environment. Machine learning is the software that learn to detect statistical pattern within data itself. Artificial neurons is the building blocks of a neural network, whereby a neural network is a type of machine learning based on a very crude approximation of how neurons work in a brain. And finally, a deep neural network is simply a stack layer of all these neural networks that can learn hierarchy of representation of data. And deep learning bring all this together through the application of deep neural networks through training and inferencing of data. Okay. Now, before we move further on, I'll just briefly go through roughly what is behind the scene of how neurons work in a neural network. So this is one single artificial neuron whereby there are three inputs going in, which will map into the desired output value. Within a neuron itself, every input will be paired with a weight, and all these weights will have a bias value that attached to it. In a neuron, it has two functions that dictate how these inputs are mapped eventually out to become the output value. So one of the function is a linear function, which fundamentally sum the input multiplied by its weights and the whole lot add to a bias. So this is a linear function. Now, the second function is the activation function. It's a non-linear function. This function maps the first linear function together, it will then provide the value to the output. So throughout the entire, say, training of this neural network, the parameters of the weights and the bias will be modified until it stabilizes and converge to the desired output that we are going for. So fundamentally, this is how a neuron will be trained throughout the entire process. And when you put multiple neurons together in a layer like that, you form a single neural network layer. And when you have more than one layers, whereby you have the input layer to front it and the output layer that leads to the output values, anything that in between are the hidden layers. And and if there are two or more, then this form a deep neural network. And when you train this deep neural network, this is a process of deep learning that we were talking about early on. Okay, so this is very high level. Doesn't cover much on the actual max set driving. I hope this is good enough for you guys. Okay, now before we move on further on the various methods and concept of machine learning as it is, I'll jump straight to a demo to show you a very simple artificial neural network, how we use it to predict the wine cultivator type. Okay, just give me a second. Okay, I hope you can see the Jupyter Notebook on my Chrome browser. So, Panja, can you see it?
Yes, we can see fine.
Okay, cool. Thank you. So now I have here a what we call a Jupyter Notebook. Is fundamentally a both an editor and a Python programming interpreter. What it does is that it will allow you to run to multiple cells. These are cells whereby it will run through the Python programming interpreter and return the result as you run through it. Let me first run all the cells one shot, because some of the cells could take a while, especially the training part, while I go through them briefly. So what we have here is that we are leveraging a library known as scikit-learn. This is a short form of it. It is a very popular and very useful libraries with functions that allow us to perform especially traditional machine learning techniques. There's a lot of models that you can use to apply. And the best part is it also comes with a few so-called toy data sets whereby you can immediately leverage to play with it, to learn and improve and experiment with various library functions that come with it, as well as machine learning techniques. So this is what we did here. We load the so-called wine cultivator library, and we put it into a Panda data frame. And this is what the first few rows look like. Basically, if I remember correctly, there are 13 columns of data varying properties of what each wine would be like based on these measurements. And the cultivator is the target or the prediction that we like to learn and then eventually predict. So by all these are just simply processes to verify the kind of data that we have. And right here are the standard process on splitting up the data into a training set as well as a holdout set. And here is just standard processing to standardize and normalize the data that we're going to feed into the machine learning model, especially when we are working with a artificial neural network, because it's pretty sensitive to data that are not normalized. By normalized data or standardized data here, we are referring to, say for example, you have two different features of a particular observation, whereby one could be range between say 0 to 1, and the one have a much larger range, like say between 10 to 1 million or 10,000. So a neural network will be very sensitive to such big different swings in the range of the data. So we have to normalize it such that the entire suite of input functions, also input data, will fall within the same kind of range, variance, and mean. So that's what we did here. So we try to put them to, in this case, between 0 and 1, and then scale it whereby the mean is, sorry, I take that back. Yeah, the means are the same. Okay, so this is what we did here, some sort of processing, and this is the actual training. Now, the good thing about scikit-learn is that it has, apart from the traditional machine learning techniques and models, algorithms, it also have a very basic but functional neural network algorithm, which we have imported here. It's called MLP classifier, and we train it using simply just 3 hidden layers. It's very simple and run through about 500 iterations, and it has already completed, if I'm not wrong, maybe within a couple of minutes. So this is the cell that does the prediction based on the model that has been trained, and we can evaluate and see how good the model is. Now, this, although we have not touched base this yet, which I will go through later on, this is a supervised learning technique on a classification subject. So we are trying to classify what is the wine cultivator based on the 13 different measurements for every wine input values that we have in this data set. So the way to evaluate a classification machine learning project is to usually look at things like the precision, recall score, and F1 score, and we use a confusion matrix to determine how well the model has done. And in this case, it did a very good job. Most importantly, if we look at precision and recall, when it comes to classification, you would like to think about whether how badly it return a false positive against your true values that was predicted, or how badly he has returned false negatives against the true values that your model is predicting. So precision is the one that look at how much, how many false positives are there against the predicted values. So the lesser the merrier. So the the value is inversely proportional to the lesser your false positive, the better the result. So one is a very good result. As for recall, it is looking at the predicted results against how many, inversely against how many true negatives that you false negatives that you have. So same thing, just a precision. The higher the value, the better, ideally one. So in this case, turn out that for this model that we use to train, a very simple three layer uh, neural network was able to return very good numbers. Okay, so you can there's so that's it. So this is a very simple way to try out the deep neural network using scikit-learn library and using the already inbuilt database or data sets that come in scikit-learn. Okay, very simple, and there are easily about 6 or 7 more such data sets within the scikit-learn library, and you can just experiment with it just like that, just a few lines of codes. Okay, so okay, I'll go back to the slide. Just give me a second. Okay, uh now okay, okay, now there are, when it comes to machine learning, there are uh well, there are 3 or 4 different learning methods depending on who is referring talking about it. But generally we will look at the 2 types of machine learning that are the ones that you use most often. So one of them is known as supervised learning. Basically it is, sorry, the other one will be unsupervised. Basically it is about how the data is presented and fed into the model. For supervised learning, you will have the um, data being labeled, whereby the model will learn how to predict a labeled data set. By labeled data set, what we are referring here is that, for example, the early on demo that I show you, you'll notice that apart from the measurements of every input value, we also have a target column whereby it says the cultivator value, where it ranges from 0, 1, and 2. So that is labeled data. So you know that every row, what it is being classified as opposed to an unsupervised learning, the data doesn't contain the label target value. So when you feed the data to a machine learning model, it will not have the benefit of knowing what are the target values. It doesn't know that a arbitrary row is of which wine cultivator. So unsupervised learning is up to the machine learning model to figure out what is the pattern, what groups them together. As supervised learning, you know ahead that the data is grouped exactly like that, is classified exactly like that, is predicted to be exactly this value, and you train the model to recognize this pattern and then predict new based on new predict new input data uh, in that way. Okay, so now supervised learning come in 2 different flavor. One is a classification, which is the first demo I have shown you, whereby when we train with the features plus the labeled target data, when given a new input value of features, we expect to now know how to predict what label it could be. So like the earlier model, the training score was pretty good. So that will imply that if you feed new data, it will be able to predict the correct classification. As for regression, it's usually applied on target value that is of um, numerical values, whereby you will predict, like for example, possible future market data value, or even something simple as, say, you were presented with maybe just 2 set of data, weights and height, and you trying to predict height based on someone's weight. So something like that, whereby the height can be a discrete or continuous numerical value. So that's regression. You predict a number. Classification, you try to identify and classify what category this thing is. Okay, and these 2 falls under supervised learning. So to demonstrate further, we'll look at something fun. this will be a image classification of clothing fashion. So just bear with me. I'll switch back to the Jupyter notebook. Okay, I hope you can see this. Oh, okay. Hmm, okay. Let me read like what I did earlier on. Let me rerun all the cells ahead of it, because the training for this will take a bit longer because the data set is a little bit big. Now, what I have here is the using the library known as TensorFlow and its API layer known as Keras. Historically, Keras used to be a library on its own, but I guess since a couple of years back, it has been now part of TensorFlow. And TensorFlow is the open source, I would say, deep learning library from Google, whereby it performs very low level uh, calculations on a mathematical kind of objects known as tensor, whereby Keras is a higher level API encapsulation library that allows you to use the to work together with the TensorFlow to build and train and inference using the deep learning techniques that we learn. So usually we are using Keras library on top of TensorFlow. Okay, so in this case, likewise, um, Keras itself, actually TensorFlow itself, also have toy data sets that we can load and experiment and try out, things. And we, for today, for this demo, we are loading the famous MNIST fashion data set, whereby the data set, I think, has about 60, 70K of data, each of which is one of the 10 type of different clothings or accessories. And just like the early on demo, we are to identify um, which type of clothing it is uh, based on the images that's loaded here. So now I'll just go through briefly through the cells. So for the first cell, we simply just load the data. If you try out, you'll take maybe under a minute, because it's quite a huge data and you literally load it across the web. And then we did a standard of scaling the images, because these images are okay. Images data usually are in the form of the either the grayness of the pixel of an image, or the color intensity of an image. So each image, as if you understand, have a is formed by pixels, and it can be a range of, say, maybe 1024 to 768 pixels, and every pixel will be represented by either one number for gray, so 0 to 255, whereby 0 is, if I'm correct, is should be black, and 255 is white, and anything in between will be gray. Or if it's a color image, then it will be represented by 3 numbers instead, for the combination values of RGB, red, green, and blue. So that's how it works. So if you're working with images that are grayscale, then every image you only need to worry about the single value of grayness for every single pixel in the image. And if it's color images, then you times 3 to that, because now you're working with red, green, and blue. So there are 3 channels of color intensity to work with, along with the number of pixels in the image. So an image file and an image data set, an image machine learning model can be large in general. But fortunately for us, this data set is not too big, because they make it small so that it's easier for us to learn. It may be very fuzzy, but it's still clear enough to tell what it is. Like for example, below here is one of the image. It's basically a looks like a sport jersey, right? So very powerful. It's very useful for us to learn how to work with classification of images. So now, so this is just more data processing to make it ready and able to be used and fed into the machine learning model, which is much further down here. So this is a model that we are using. Without going too much into the details, technically this is known as a CNN deep learning model. The name is representing convolution neural network. So usually when it comes to deep neural network technique apply on say identifying the kind of image classification, or to even say detect an object within a picture or a moving video, we would leverage on a deep learning technique called CNN, or convolution neural network. So the technique involves using a CNN block like that. So there are 2 blocks here with further so-called processing of the data, and this whole thing form the architecture of this model. So you have the input layer, a couple of convolution and pooling related to the block, so that makes it 4 layers here. 1 layer to flatten out the data. This is a regularization technique. You use it in order to make sure that the model is not too biased to the trained data. So usually you have 1 or 2 of these somewhere here. And then finally, this last part is the output layer. So because it's a classification, so it will have only, this layer only have like the same number of neurons per layer. So in this case, I believe should be 10. So is the trend. This is the look and feel of how this architecture look like. And important numbers to take note of is this is the total number of trainable parameters. These parameters relate back to earlier when I briefly talk about how the neurons uh, 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 calculate and compute. Remember the first linear function that has the sum of the weights and then added on to the bias. That these are the numbers that sum up to these parameters. This is actually a small number, 34K. Usually, deep learning techniques that apply on things like, say, complex data subject like images, these can range up to 100K or even millions. Same thing apply on complex subjects like language models. So 34K is pretty small, not a lot, technically not a lot of parameters to work with. So the training will have taken very fast. As you can see, in this case, this is where the actual training happens. So we chose to iterate over 15 epochs. That basically means you run it 15 times until it converge and stabilize to the desired output accuracy that you're going for. So from the look of it, every epoch or every run, it took only 2 seconds or less. So overall, probably no more than a minute. So this is pretty fast, especially since the case the parameters wasn't a lot. And you can see that the accuracy and the loss scores are pretty good. For loss score, the lower the better. For accuracy, the closer to 1, which is 100%, the merrier. And this first part will be the training loss and training accuracy scores. This second part is the validation loss and validation accuracy score. Usually you use both to gauge how well the model is. So in general, high score for both is good. High score only for this side is not too good, because if your training um, scores are high, but your validation score is low, that will mean that your model is too biased on your training data and cannot generalize to the validation data that you held out from the training. That will mean that if you apply to other new input data, this model will not predict very well. It only predict very well on the training data that it was trained. So generally go for high score for both. Okay. Now, so this, okay, so after 15 epoch, it did a good job. We have a very good accuracy for both training and especially validation data. And this is the overall score here, same number as this side. And to in this case, because it's an image classification, we can easily visualize and see how well it did, which is not too bad. So for the way we did it here is that when we visualize it, any red highlighted title would mean that the prediction was wrong. So the prediction are the one in the first word. The one in the bracket would be the actual true value, or we call it the ground truth. So not too bad. Out of, let me see, 15 randomly chosen test data here, when we predict it, only one was wrong. Not too bad, right? So this overall, this is a good model. It did its job. We could improve it further through other techniques to maybe get more data, maybe add 1 or 2 more layer in the model, things like that, to help improve, or maybe even use a different kind of technique or model. Okay. I hope this gives you a better understanding on um, how a multiple layer or deep neural network look like, and this is how the architecture usually is built. And in this case, we did it on a image classification project. Okay, so now I'll go back to the slide and continue with the presentation. Give me a second. Okay, so now that was a based on a supervised learning technique. So as I mentioned early on, when it comes to machine learning, besides supervised learning, which you use label data to train the model, you also have unsupervised learning, whereby you have no label data. So the model doesn't know um, that what is classifying, and it will have to use techniques that or certain algorithm to so-called perform cluster analysis, and then try to look for latent properties within the input data, and figure out how these different uh, data are being grouped or clustered together. Okay, so
Sorry, Fan. Hi, Fan.
can't see.
No, Fan,
I,
sorry to interrupt. Yeah, before going to this, can you please look into the chat also? There are some queries from the
oh, sure,
participants. Yeah,
sure.
please answer it. Thank you so much.
My bad, my bad. Hold on. Oh, CNN bias cannot be changed. Okay, I'll answer the most recent question first. Uh, Not really. Um, we we flatten it only because in that case at the it's not at the fifth place. It's actually just one step before we pass it on to the output layer, whereby that's where we try to classify which of the classification it belongs to. So we have to flatten it to become just one dimension. That's why the flatten is left there. And I think what you're trying to say here, when normally we put it at the first layer, that is only if the input data was not a flattened data. In our case, the toy data set that came with carrots is already flattened for us. So that save us the trouble of flattening right at the top. I hope that answers it. Maybe I'll answer one more question. CNN biases cannot be changed. I'm not too sure what you mean here. Maybe if you can private chat me, I'll try to answer you that question. If you can elaborate further what you mean by CNN biases cannot be changed. Let me look at one more. Okay. Nisha asked about explain the meaning of generalization to the context of ML. Okay, I think I mentioned earlier on just now, right? This is a fundamental machine learning concept whereby when we train a model, whether be using a traditional machine learning algorithm or even a deep learning algorithm, um, we want to make sure that the machine learning model that you eventually have, your final model, it will generalize ably and in a robust fashion to predict um, data that he has not seen before. So that's why it's important that you do not focus purely on getting very good results, be it based on accuracy, F1 score, depending on what you were working on. Do not aim for just merely very good result on the training data itself, but it must also achieve reasonably good result with unseen data, or we call it holdout data, or in our case, we call it the validation data. That's the data that we validate that the model that you train is able to generalize and able to predict data that it has not been trained or seen before. That is key, right? That is key. That's what I meant just now by about generalization of the machine learning model. Okay. 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 If there are any other questions, just go ahead and put up in the chat, and or if you can private me separately if there's something more you need to elaborate. I'll carry on with the slides. Okay. Give me a second.
One more question have Fan, just the last
Yeah.
one from
Sure.
Nisrin, I think from the first notebook,
Where is it?
the
Uh,
last chat.
Last chat. Okay, sorry. From the first notebook, please explain the arguments passed in the standardization function. Okay, give me a second. Let me jump back to the first notebook. Uh, the standardization. Oh, okay. I think you're referring to. I'll put in the chat, so that I think you're referring to this, right? So fundamentally, hold on, so so just bear with me a second. Okay. Mm, okay, actually, if I'm not wrong, those are actually the default settings that come with it. So maybe I'll come back to you on this. I I forgot why I put it there, because by right we need not even put in the values. These are the default values. If you want to change it, then you actually need to specify that you want to be false for each and every one of the variables. But in general, if you leave it as true, which is the default value, then the let me see, it should center around, if I'm not wrong, the mean should be 0, not wrong. The variance should be 1, but I could be wrong here. Let me double check. I'll come back to you on this. Okay, sorry about this. There will be Nisrin, right? Okay, got it. Okay, now okay, so let me go back to my PowerPoint. Oh, I haven't shared out yet. Okay. Hold on. Okay, I hope you can see this. So as I was saying, this I was talking about the unsupervised learning, and one of the method is known as cluster analysis. So I will move to the next demo, which leverage such techniques to work on movie recommender. Okay, so let's give me a second. Okay, hold on. Where is it? Okay, number 3. Okay, so sorry, my mistake. This is the one. Okay, let me run the I should have, sorry, have I shared it? Oh yes, I have. Okay, so let me run the the cells first, because this one can be a while. Okay, then I'll go through the cell a little bit closer. So again, we are leveraging TensorFlow and Keras, and also let me see. Oh no, sorry, I take that back. Mostly just Tensor and Keras. So same thing. In this case, we load a data set that is from a different source, and we unzip it and sort of read it in as a CSV file. So eventually we have a pandas data frame that consists the data set that we downloaded from a other website. So what this data set does and perform is that it try to look at all the different preferences of movies type, right? Genre and all that, of all these users, and based on this data set, without telling it specifically that which group of user or which cluster of user prefer specific range and genre of movies, and then Now you post it a new user with a very specific selection of movies that he or she like with a certain ratings, usually 1 to 5, and then recommend based on the database that you already have what movies that he or she might like further. So this is a clustering technique that we apply here. Okay, so all these are mostly just some sort of a EDA to exploratory data analysis to look at what kind of how many numbers of users are there, how many movies are there, and what kind of ratings we're talking about. So in this case, minimum rating is 0.5, maximum is 5, and these are the standard preparation of the data to split it up in between training and a whole out data, or in this case, a validation data. And this is the model. So it's okay, it's a little bit complicated here because this is based on the uh, embedding technique, whereby we use this thing known as the embedding tool. How to put it? Combine the preferences of all these multiple users into one matrix, and then we train this model, and using this model itself try to predict what a new user would prefer based on his or current preferences. So the current preferences are based on the ratings that he or she give to some of these movies, and it can be quite accurate to some sense. So for example, in this case, this is a randomly chosen user, whereby he or she prefer movies like that, and based on the overall database of all the other users preferences and ratings that they give, and these are the recommended movies for this person here. Yeah, so and it can be more, just that it only lists out the top 10 because the closeness here are the closest to what the user would prefer. So let me see. Yeah, so in this case, the training took only about 5 epoch, but it was enough to derive a decent training accuracy. But in this case, we are looking at the losses, because this is a unsupervised training technique, whereby you don't really able to evaluate using accuracy, because there's no label data. Without label data, you cannot validate how evaluate how well the prediction model values compared to the true value, which doesn't exist in this case. So what we do is that we indirectly look at how well is the how low are the loss scores, determine whether the model has converged to our desired values, which in this case usually the loss scores should uh, go down this way. So it's not too bad. The training is the one in blue. The validation or the test is the one in orange. The lower the better, of course, but in this case it's not too bad. So that's why if you look at an example here, based on what someone like, these are the movies that should be similar to what this person like. I can run this again. You will select randomly another user, and if you can see, yeah, sort of close to what this person like. He likes some sort of sci-fi movie here, action, and there's a couple of sci-fi here, right? No, couple of action sci-fi and all that, right? It's pretty similar. Okay, the key thing about this is all about similarity, right? Okay, so okay, let me hold on. Let me check whether there are any chat first. Okay, let me stop this. Okay. Oh. Hmm. Okay. Embedding is how to explain in a more layman way. Okay. I'll leverage the concept of a little bit of matrix or well, yeah, matrix, linear algebra and matrix. So now, when we work with machine learning, whether is it traditional or deep learning, um, we work with matrices and tensors and vectors and things like that, whereby say for example, let's go with just a single value to of features. Say my one of my simple example I mentioned earlier on. Let's say you have a data set of weights and heights and trying to predict someone's height based on someone's weight. So weight will be your feature, will be your the input value feature that you want to use to train a machine learning model, and hopefully you come up with a finalized model that can then predict correctly unseen data, unseen weights, and predict the correct heights or projected height of this person. So that's one value, right? So you if you use the matrix, you will have a basically um, a vector of um, a column vector of the weights of multiple rows of the many uh, different person weights passed into the model as a input very data. So for every row represent the measurement observation of uh, one or more person, and every column represent the features or measurements that of that particular feature. So in this case it's weight. So this is one column, one single feature. So if you generalize this to more than one feature, say now you have maybe age, right? There will be two features. So now your vector has now become a two column by maybe n number of rows. So and you can grow, right? The more features you add, the more column you have in your matrix, and and if you have say 13 features or more, then you have 13 columns or more in your matrix, representing the data that you will send into your machine learning model. So for something as simple as that, 13 features, 20 features, these are nothing. The key thing is that the number of features must never be more than the number of rows or observation of or input data that you are feeding in. Now, when it comes to things like, say, for example, images, complex data like that, or NLP, natural language processing, that you look at languages, text. When we transform this data into a usable numerical data for machine learning to work, the number of columns, right, which we use as features for our input for the machine learning model will be a lot of features. So say for example, when we come to the pictures that we're working on just now, images, those images were about 64, sorry, were, yeah, 64 by 64. That's that's easily about say 700 something number of pixel. When you flatten it, that will be your number of features per row, right? So that is a lot of features to work with, and with much larger images you will have up to millions or millions of features, and this will mean that the features may be likely more than the number of rows of input data that you're feeding in, which is not good. It will mess up with your machine learning technique. So that's one. So text wise is the same. When we transform text to make it uh, uh, to numerical data so that the machine learning model is able to digest it and look for the patterns. We use something known as an embedding technique to um, reduce this number of features from, say, millions of columns to much lesser, say maybe 200, 300, number of columns. Uh, Embedding is one of the technique within machine learning, especially in this case, deep learning, that will help you to um, em well, the word is embed, to embed the latent patterns and uh, uh, um, properties from millions or hundreds and thousands of features down to just a manageable size of 200 or 300 features, um, through very clever mathematical transformation, whereby they reduce that size to a much smaller vector. That will help with then feeding it into the machine learning model, and it can still then distill uh, patterns that's within it, even though he has now shrunk the size through a much smaller number of columns, from millions to maybe a few hundred, through the technique of embedding. I hope that helps. Okay, okay. Now, I'll move on to quickly to the next slide. Just give me a second. I'm pretty bad at this. Okay, hope you can see it. Okay, so that was demo 3. Oh, sorry. The next slide is about demo 4. So early on, the third demo was about a movie recommender based on the ratings of all the users that all the ratings that users submitted before, and then a user come along. He or she has his own current set of ratings, and then using the unsupervised technique clustering, we try to match similar group of users. Their preferences, their ratings are similar to the new guy, and then show him what are the top 10 movies that are similar to his or her ratings, right? That was unsupervised. So now for demo 4, we will go into more on NLP, natural language processing, but this time to predict whether a movie reviews written in text, whether is it a positive or a negative sentiments. And this will be a supervised classification machine learning technique. Okay, just give me a second. Let me switch to this. Oh, okay. Okay. Let me run this whole thing. This one can take a while. Okay. Now this also is based on a data set that is, if I'm not wrong, already in TensorFlow. Yeah, based on the IMDb movie review sentimental classification data set. So we again leverage TensorFlow and Keras, the high level API, and we load the data in. And again, because in this case, we are trying to do two things here. First, we need to as I mentioned earlier when I was trying to explain about the embedding, we trying to transform the the uh, the the text of every entry, every row of the these movie reviews into a manageable vector. So we use the embedding feature within Keras to do that, right? So that's one. And then in this case, this is a bit high level technique um, which I won't advise you to trial immediately. I'm just sure. I just want to show you that it's possible. Simply just 2 lines of code. Whereby this is something known as a bidirectional LSTM. Just 2 lines to build a deep neural network to classify based on this text input. These are text input. Based on this text input and the label target of value, either positive or negative sentiments. And then once it's learned that, when you feed in new data, it will be able to determine that the review is giving a positive or negative sentiment vibe. So
Have
um,
fun.
yes,
Sorry to interrupt.
yes,
I
sorry,
think you're sharing wrong notebook. It's still
oh
collaborative filtering movie lens we are seeing.
really, oh so my bad, my bad, so sorry. uh that's strange. Hmm, hold on. Eh, are you seeing the right one now? It is a bidirectional LSTM.
Yes, that's correct.
Okay, I'm so sorry. Sorry guys, very bad about this.
Yeah, please,
Okay,
please start from the
okay, I'll start from the
start
top.
from
Yeah,
yeah.
so sorry about that. Okay, now I've already run this notebook, which is good because the model is really in this case uh, more likely because the features are a lot, and it will take a while to train this. I remember it's about 4 or 5 minutes per epoch, but it's not too bad because of the model that we use. It kind of shrunk it down to just a need of maybe 1 or 2 epoch to finish it. So like I say, we are leveraging again carrots from TensorFlow and the IMDb toy data set that come with TensorFlow, right? This one, and we are to perform a supervised classification. Sorry, supervised classification machine learning to identify each and every entry of movie review which are in text, whether this is a positive or a negative sentiment. So based on just what is written in the movie review, and based on the label that is already sorry, based on the target that is already labeled clearly, and learn that uh, what are the words that show that this is a negative or this is a positive review, and then when you feed in with an uh, unseen review, it will now able to predict accurately that this is positive or negative sentiment. And the technique here we use is a little bit advanced. Like I say just now, it use a couple of things here. Like I say, firstly, embedding, as I mentioned earlier on, it helps to shrink the amount of features, that when we work with text, we use embedding to shrink it down to a manageable vector, such that when we feed further down to other layers, the machine learning model will be able to learn it more efficiently. Now, the machine learning model here has only 2 layers because it leverage very cleverly using this thing known as a bidirectional LSTM. Now, ignore the bidirectional first. LSTM is one of those commonly used, I would say, important model technique to to derive uh, uh, patterns and that kind of thing from, usually in this case, natural language. So just like CNN, which is the normally go-to, like the convolution neural network that we used earlier, CNN normally is the one of the technique we normally go to build a model to identify an image. LSTM, which is a technically a RNN technique, a recurrent neural network, uh, whereby LSTM stands for long short-term memory. Uh, we normally use either RNN, LSTM, and one more known as GRU. These are all RNN techniques whereby they have a very special flavor to it, whereby unlike the other models that we apply, like say CNN or even just a normal dense layer that we build into the hidden layers, those are, we call it what call it, forward feeding neural network, whereby the neural network, every layer doesn't know or remember the values from the previous layer, right? With recurrent neural network technique, RNN, LSTM, GRU, in this case RSTM, that's why the word long short term is there. It kind of is designed in a way that it can learn based on what happens before, what was the parameter values that in the previous iteration and that kind of thing. And bidirectional here means that it remembers both ways, forward and backward. So that makes it really powerful, but it also end up using way more processing power and if I'm not wrong, probably a lot more parameters as indicated here. Look at the number of trainable parameters is 2.7 million. Simply just 2 lines of code and a simple embedding of 128 here. That blows up to this much of parameters in the train, right? But because of this incredible method, a bidirectional LSTM apply on text, natural language, it works. It works very fabulously, and the score should be pretty good. Oh yeah, there you are. So as you can see, both the training accuracy as well as the validation accuracy are pretty high. They are in the range. Oh, sorry, I should look at the last one. They are in the range of 90s and 86%. These are very good numbers. Okay, so I uh, I then did a simple classification report to evaluate how well it did. And like I mentioned earlier on, when it comes to classification, you look at precision and recall. Once you check against how much false positive are there, the lesser the better. So the higher the precision value is, the better. And how much false negative values are there. Likewise, the lesser of false negative values are there, the higher the recall rate will be, right? F1 score is just a harmonic mean of these two values added and multiplied together. So normally we look at all these 6 numbers to gauge. Okay, I take it back. I look at all these 3 numbers to gauge how well each of the category or class that we were trying to predict. In this case, it's a binary classification. There are only 2. We're trying to see whether is it positive or negative. There are cases whereby you are looking at more, right? Like you're trying to classify maybe what kind of breed a cat is, what kind of breed a dog is from images. Then you might have more than 2 classification, and then that is when you want to make sure all these numbers for every single class or category returns you good numbers. Okay, cool. So I think that's it for the demo. Now let me see if I have any more question. Oh, sorry, can you guys still not see my notebook, or that was earlier on messages?
That was for early messages.
Okay, okay, okay. The one before that, what is the input features for train a model for unseen data prediction in movie? Oh, that was my bad. For train. Oh, okay, sure. That is an interesting one. Let me just simply switch. Oh, sorry, where's my mouse? Okay, let me just switch it over. That'll be notebook 3, right? So you're asking about what are the input features, right? Let me see. This is movie recommender. Oh, okay. Hey, I forgot to show this. Let me see. Okay. Well, the features are here. Let me just open up one. I hope you can see it. So this is a feature. See, just like that. So um, there are multiple users, and these are the ratings they give to different movie. So basically, you are looking at um, um, data whereby as long as it has a combination of these three, sorry, I'll say these two, a user and that means a unique combination of the user and a movie plus what is the rating the person give to this movie. So so you are basically this whole database is just that. So it could be that a user maybe only gave ratings to just one or two movies, then you only have one or two rows of that particular user with one or two movie rating. But if the user has watched a lot of movie and provided a lot of ratings feedback, then the user may have a lot of data here, a lot of rows with the user ID, but with many different movie IDs along with its respective ratings. Okay, so this is the data set, how it looks like. And it's really pretty clever because it doesn't depend heavily that every single user must provide a ratings for every movie, whether he or she has watched it before. It's simply based on what you have seen so far, what ratings you have, numbers you have provided so far, and yet it can still find similar. Okay, it can still look for the clustering pattern within this group of data, and then when come along with a new user with a set of equivalent movie and ratings. Maybe this user come along and just submitted say 5 to 10 ratings for 5 to 10 movies. Is enough to generate some sort of similarity search and recommend you uh, what are the movies that are similar to you based on all the other inputs come from the other users. So this is a very clever technique. I hope this answer your question. Now they get to see the input features. Okay. Okay, cool. Okay, let me now go back. Okay, thank you. So let me go back to the slide. I think we're almost at the end. Just give me a second. Okay. Okay, I hope we can see this. So so we just concluded the demo 4, which is a supervised learning technique on classification of text input, right? And it's a binary classification. Because you only classifying and predicting positive and negative target values. That's all, right? Okay. So now, as I mentioned earlier on, um, deep learning has a lot of many other techniques. Things that I didn't even cover today is like reinforced learning. That is there's a totally a different branch of machine learning. Normally, we classify that as the third or fourth type of machine learning, along with supervised learning, unsupervised learning, and sometimes we include semi-supervised learning, and reinforced learning is among that level category, right? Reinforced learning is very different from the supervised and unsupervised technique, whereby the model learn through a reward system. This is the fundamental technique that drives, especially those how you call it, those deep learning models that you see mentioned in the news behind gaming kind of environment. The one that I mentioned earlier, AlphaGo, right? The Dota and StarCraft and things like that. They even apply reinforced learning technique in things like, say, if I'm not wrong, poker, etc., etc. So those environments are unique, whereby the data are streaming in. It is there are unknown factors sometimes involved, and reinforced learning are and usually the rules are not even mentioned sometimes. And reinforced learning through its incentive reward method allows a machine learning model to learn and become good at doing performing in that arena. Okay, so I won't go too much into it because it's really a very even a much more difficult concept to elaborate. But just understand that this is the one of the fundamental technique or algorithm or model behind usually in those gaming environment. Okay, so and we mentioned earlier on convolutional neural nets, right? How it's been applied, and usually in the area or genre of things like say image processing or object detection, things like images. You can actually also use it on languages through a one-dimensional version of it, but rarely. So normally with languages, we will use recurrent neural networks more because it's able to remember things before. And if you work with bidirectional version like bidirectional LSTM, it can remember things ahead. And um, the advanced version of those would be things we might heard of in the news, like if we heard of GPT-3, it all those leverage even more advanced technique like transformer attention, whereby the models are really complicated. The architecture will be very long. Early on, those architecture that we print out a summary, they last only like 3, no more than 5 or 10 lines, right? The really complex models um, that that hit very fabulous numbers, those could numbers by hundreds to 200s or even I think I've seen 300 to 500 count lines. So they actually all fall back to the fundamental blocks of leveraging things like recurrent neural networks. Okay, but they build on top of it, and they put in different layers of how they manage it, and then multiple blocks on how they eventually come up with a architecture that is so fabulously powerful. Cool. Okay. Um, okay, now, sorry, and one more again, which I guess most or some of you might have heard of it. It stands for generative adversarial network. Is is famous for being able to generate new things by simply showing it that this is what it looks like. So usually you come across it a lot nowadays. Pictures, right? You show this model a bunch of pictures, lots of pictures, like celebrity pictures, and it is able to learn the latent properties, the latent unique features within this bunch of pictures, and generate new pictures based on the features that it's learned. Maybe most of them have some sort of thick eyebrow, thin eyebrow, some wear glasses, some don't, some have mustache, some have beard, some face are sharp, some have maybe different color eye, and then it came out new faces based on those properties. And and over the years, especially recent years, it become more and more successful at being able to come out so real that you almost, in fact, you almost couldn't tell anymore that it's not a real person. So pictures is one, sound is another one, right? Audio, they can fake audio of almost anyone right now if you have the right data, enough data, and the enough computing power to do it, right? Things like that. And
Hi,
yeah,
Fan. Hi,
yeah.
Fan. Sorry,
Sorry.
can see just blank screen. Are you sharing anything?
Oh, sorry, blank again. So bad. uh, could it be this one? How about this? Can you see it now?
Yeah, now we can see.
I'm so
It's
sorry.
more on AI.
I'm very sorry about that. Okay, so I was saying, yeah. So that's GAN, right? That's generative adversarial network. Um, it's on its own almost a very advanced topic. It involves very um clever technique of training two competing neural network. Fundamentally, that's what it does. Um, it train one network to learn how all these features of the input data are, and then generate fake data out, like a fake image or fake sound, fake music. And then it use another network known as a discriminator to criticize uh, and give a score to the first network, and the score will determine and sort of like feedback to the first neural network on where it's done wrong, where it's not good enough, where the second discriminator neural network able to figure out that it was a fake target, it was a fake image, fake sound, fake music, and then the first network learn from this mistake and try to generate even better images, better sound, better, and it goes to and fro. It literally just goes to and fro like that. Eventually, it reached the point where discriminator can no longer give a high score of bad data being generated. Now it's all just low score. So that's how it works. Roughly, this is just a very high level concept. And there are even many different variants of techniques within GAN, how it's been done. It's really advanced stuff, but really very wonderful that where this is going along. Okay, cool. Okay, think I think that's it for me. Okay, good. So what we have learned today. So briefly, deep learning is, as I start from beginning, is about teaching machine to learn how to identify patterns in data and learn how to rationalize based on the surrounding or environment, and and it is built on the fundamental of artificial neural network, which based on the ideas of biological neurons of a brain. So you have a concept of how a neuron work. We have input going in and output going out, and you have functions within the input to work with the parameters like weights and biases, and then you have multiple of such neurons within a layer, and have multiple layers of such uh, 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 neurons, and then you train this. Eventually, if you have a good model, you have enough data, it will converge and stabilize to the right parameters and weights and biases across to provide a model that is able to robustly give you the prediction and result that you're going for. Okay. I think I think that's it. So if there are any questions, feel free to ask. I think let me check. Oh, okay. I think Nishrin, you asked me a question that you copy from Jason Chong, is it? So okay. Oh, okay. So you're sharing something with me, right? If you have a question, feel free to put it in the chat. So anyone else has any other further question? If not, then thank you for joining me today. Back to you, Panja.
Thank you so much, everyone. If you have any questions, please feel free to ask in the chat box, and Mr. Fan will answer your queries. And so we'll be here for a while, just for a couple of minutes. So just type your questions in the chat box.
Okay. Maybe I'll intercede. I see that Nisha asked me the fundamental use of an LSTM. Okay. So usually the most commonly used of LSTM is in the area of natural language processing and NLP. So because of its unique ability to be able to remember, it has a memory of what happens before, right? It remembers values that will happen what happened before. So LSTM, GRU, that's another one. I think it's gate recurrent unit, I think. And of course, they're all part of the family of RNN, right? Recurrent neural network. All has a similar overall feature whereby it has the capability of remember values from before, and if it's bidirectional, it is able to uh, uh, carry forward to backward the values that it currently knows. So that, for example, why it's so applicable for text, it's like unlike input data from other kind of data set. Languages is unique, whereby if you look at the line, right, look at, for example, the statement you ask, what's the fundamental use of LSTM? When you feed this information as a data, right, you transfer it into data. In machine learning, we normally use vectorization to transfer each and every word into a recognized number to the machine model, and these data are as per se. So say for example, I give a maybe I use a technique called count vectorizer. So I'm counting number of each word that's short in each of this line. So what is one, uh, and it has an index of say maybe 0, for example, that represent what. Then the maybe index of 2, it also has a value of 1, and vice versa, and so on and so forth. So I have a series of such numbers, and it's just numbers to the machine learning model, right? So it's just a number saying that this word occurs how many times in this input data in this row, but it doesn't show you, or it doesn't show the model the relationship of these words against the other words that went before. And that means a lot when it comes to language. So in language especially, the values of the words in relationship before and after, even before 2 words ago, 3 words ago, will have a certain meaningful call that pattern or latent values to a machine learning model. So that's why we use um, uh, techniques like OSTM, RIN, or GRU. These are one of the these are the family of algorithms whereby it will keep track of the words that has gone before or that will come after. I hope this helps, right? Where opposed to other technique that you don't need to rely on this. In fact, I don't think you ever utilize RN, RSC, and GRU on say on an image, because you don't need to. Image make use of CNN to, in a way, figure out what the images is like. That's a totally different thing. Or you don't apply on a regression thing, regression prediction, whereby say you have features like weight, age, height, to predict someone maybe BMI. You don't need to know what has gone before and after. They are just numbers as per se, per column, per feature, right? So for languages, it's unique. You make use of technique like LSTM in order to not only learn um, uh, the um, the value of this word, how many times it show up in the sentence, it also is positioned relative to the other words in the sentence. That helps a lot for the model to figure out, well, in some case the sentiment, in other case to classify it, right? Okay, so thank you. So anyone else has any other questions you'd like to ask?
Okay, everybody, if you don't have any questions, then we can actually, you can just go and see the recorded session also on the our YouTube channel. So please go and subscribe for the recorded version to get it. And also in the description of that channel, we will put the link from where you can get all the notebooks and the content for today's session. So please just go and subscribe it, and then we'll do. Okay, fine. We have one question from Aditya.
Okay, how do we deal with outliers and class impairs? Oh, very good question. Very good question. Okay, um, I'll answer them separately. These are two different questions. For outliers, outliers normally you dealt with them during the right at the start, during maybe around the pre-processing, or even further early on, around the minute you extract and load the data. So during those moments, you have a process known as either or, initial EDA and EDA, whereby you do uh, exploratory data analysis, you want to make sure that your data is clean, is robust, is ready for input into the machine learning model to be trained, right? So that's where you find out whether there are things like any missing data that suspiciously look like outliers. I just put it outliers, meaning that this data may not seems to be belonging to the rest of the data in a similar trend or pattern. Could be due to maybe human errors, right? The data could be wrong because of human error input, or it could be due to machine error, or it may be due to many other reasons that along the way, when the data reached you as your data source, that data suspiciously could be wrong for the machine learning model, right? So um, when you come across outliers like that, right? Uh, in general, the guide, well, the guiding principle is that if it's negligible, right, you will just drop the data. So you could be dropping a row of data or more than one. So unless your data really is not clean, it's really very bad, then in that case you have to definitely go back and go back to the source of the data collection and make sure nothing is wrong there. The collection is correct, the input is correct, and then work from there. Usually you should not have a lot of outliers, right? You should have less than less than maybe so less than 5, less than 10, and these are something that you can afford to drop, because normally your data should not have anything less than say 50, 100 or 1,000 data values. So dropping away 5 or 10 rows is fine. It won't impact you that much, right? So you have to usually gauge accordingly. Do not drop so much that you left very little data to work with. Yet you must drop it, because any outliers will definitely skew or bias your model, right? So that's not good. So usually you choose to drop it. And this is in terms of outliers, in terms of row. Um, Columns wise, although we don't call it outliers, you might drop columns too. That means you literally drop a feature. It could be, that means a whole range of numbers that you do not want anymore for the model, maybe because it doesn't correlate well with your target value. So things like that, you will also choose to drop if you judge that it doesn't work, it will not work well for your model. That means it doesn't correlate well with your target value, or it 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 no, this is a linear regression thing. It will correlate too well with other features. Then you should not have redundant features that uh, represent almost the same patterns and 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 trends. So you should consider dropping one of them if two or more features are of the same correlation, or they are correlated to one another. So that's another thing you need to consider. That's not outliers. Okay, outliers you're talking about rows, not talking about features in columns. So as for class imbalance, this is a pure classification things that you have to watch out for. Class imbalance, it now depends on very heavily on what you want to derive from this machine learning classification process. To You have to now balance between the need to either get a model that is good at driving down false positive. Sorry, I take that back. You're talking about class. Oh yeah, yes, correct. Still the same. Talk about driving down false positive or false negative. So when you have imbalanced data set, you have two things you need to worry now. You have to figure out, on one hand, what's the balance between the precision and recall scores that you want to work with, and on one hand, the data itself, how imbalanced is it, right? If they say, like, say for example, we are talking about binary classification, one of them is about 50% of the other, it's still workable. That's not very imbalanced. It turned out that from time to time, a data set like that is still fine. So let's say you have 3 classes and one of them is 50% of the others, still fine. Unless you're talking about very extreme imbalance, like say 5%, 1%, then that's pretty bad. Then you have to consider whether that class is of value for the model. If it's of value of the model, then you have to apply uh, one of two different techniques to either I forgot the right word. The idea is to either resampling. Either upsample the number of data for the lower imbalance class, or downsample the major sample class. So in other words, you try to square off and bring the balance back between the two imbalance classes. The lesser one bring it up, or the more bring it down through resampling technique. Okay, so that's one way. But usually, unless I say if it's not too imbalanced, only 50%, 60%, right, of one another, it's all right. It's still workable, right? Then you focus more on balancing the recall versus precision based on what you need, right? What's your goal? But if it's really skewed, very bad, one of the classes have only maybe 5, and the other ones has 100 and 1,000, then now you have to consider what to do with the way much lesser sample class. You may actually need to now collect more information, more data for the class. That may be one of the quicker solution, right? Like let's say, for example, use a simple example, like you're trying to classify breeds of a cats through pictures, right, through images, and let's say you have three breeds, three pictures of three breeds of cats. One of them is super low in numbers, only 5 out of hundreds of pictures, or the other two dominant majorly. Then if you still want to be able to come with a model to uh, classify these breeds correctly, then my answer is that you must now get more pictures of the one with the low sample. That is the only way out, because it makes sense, right? Intuitively, by having more sample, right, bring up to almost maybe 30%, 50% of the others major classes, it will now uh, give you a more robust data input to your machine learning model. That's my answer to you for imbalance cases. If you can't do that, then you need to consider the resampling technique, to the point of the extreme ones, like 0 and 1 shot technique. But those are really extreme if you need to go to that level. Okay, cool.
Okay,
Um,
thanks, Juan.
yeah.
Aditya, I think it is okay, right?
Okay. Any more question? No, I guess. Pranja?
Okay, then thank you everyone. I hope all questions are being answered. So thanks again for the wonderful session, Mr. Fan, and thanks to all of you who joined today. You are really a very nice audience. I mean, I could see the questions and the way that how you interacted is very nice. So we hope that you learned a lot today. Please go, and if you want a recorded version, get from our YouTube page, and then you can refer it later also. So thanks again joining. Have a good day, everyone, and we can end up the session here.